If you have read the newspapers today morning, there was a small report from the Journal of Learning and Behavior, which reported that dogs understand their owner's emotional state. Okay? When people are unhappy, dogs do come and do their best to comfort their owner. So the point is that living beings interact at the emotional level, and there is no doubt that emotional component makes up a very important part of our consciousness. We are highly logical entities, building our work on facts, figures, and so on. But we can never discount the emotional component of our existence. And there is huge effort these days to make computers as close as possible to human beings at the emotional level also. Can you go back to the slides? No, these are not my slides. Screensaver? Oh, okay. So you'll have to. So I'll have to keep using. That's it. Okay. Okay. Right. Okay. So I belong to. There is slight feedback. Can you reduce the feedback? I belong to two institutes, IIT Patna and IIT Bombay. I am the Director of IIT Patna and Professor of Computer Science at IIT Bombay. So all this work is done by my students over a number of years, and they're PhD, master students, B.Tech students, and so on. Now, before we begin discussing the topic itself, the perspective is that sentiment and emotion analysis are part of what is called natural language processing. And natural language processing itself is known to be a multi-layer activity, starting with morphology at the bottom layer, going through part of speech tagging, chunking, parsing, semantics, up to discourse and co-reference. So we go from small units of text to larger and larger configurations. So at the morphological level, we try to deal with word. Okay, divide the word into its parts, especially what is called lemma and the suffix. Quickly, for example, is quick, and li. Li is a suffix indicating it is an adverb of manner. Then we move up the chain and do grammatical tagging on the words. We need to know if the word is a noun or verb or adjective or adverb and so on. Chunking actually groups words together. The blue sky, for example, is a chunk. Then there is the stage of parsing, which is creation of trees out of linear sequence of words. Semantics is concerned with meaning representation. And finally, discourse is connected pieces of text where pronouns have to be bound to their corresponding noun, okay, and ellipses have to be resolved. If there is a text drop, then you need to complete the text, and then meaning emerges from large amount of text. And NLP is also a multi-dimensional problem in the sense of the language axis representing multiple languages of the world. We know that languages have different properties and they have their own personalities, so to say. Language is an integral part of our emotional existence as well as culture. Then on the y-axis, we have what are called important problems of natural language processing, like parsing, morphological analysis, sentiment analysis, and so on. And the axis which is of interest to computer scientists are the algorithm axis. This is where important techniques are created, mostly based on machine learning, like hidden Markov model, conditional random field, deep learning, and so on. So this is the perspective, and natural language processing is really a confluence of linguistics and computation. Linguistics, we are quite fond of saying this. Linguistics provides the eye, and computation provides the body of natural language processing. So at the linguistics component, we have what are called lexicon, which is a repository of words and their properties. Then morphological processing is processing of words. Syntactics is processing of sentences and getting the structure. Semantics is concerned with meaning. And these are traditional components, classical components of linguistics. And at the bottom layer, we have the computational entities like graphs and trees, finite state machines, probability theory, machine learning, and so on. So natural language processing is a confluence of linguistics and computer science, and solving very interesting problems like information retrieval, summarization, machine translation, sentiment analysis, and so on. Now we come to the definition of sentiment analysis. This is because we have to be precise about what problems we need to handle and what are the components of this problem. So sentiment analysis is a five tuple task where the third entity, SOIJK, is the entity of interest. We need to know the sentiment. Okay, S is the sentiment. And the sentiment can take three values: positive, negative, or neutral. Then OJ is the object about which the sentiment is expressed. F is the feature of that object. H is the opinion holder, and T is the time at which the opinion is held. To illustrate this definition, I take this example. This is a long sentence. I love the songs in the movie, though only the cast was liked by my brother, who said the director was of the opinion that the storyline, which is from a novel by Shakespeare, will be lapped up by public. So notice how the sentence is winding through many different thoughts and how many different entities appear in the sentence. So if we begin recording them, okay, if we begin recording them with a natural language processing parser, for example, through dependency parsing. So the entity here is movie, and the aspects are songs, cast, and storyline. These are different aspects of the movie. The opinion holders are I, brother, director, and public. Though the name of Shakespeare appears in the sentence, Shakespeare doesn't hold any opinion. The time is present tense for I, past tense for brother, present tense for the director, and future tense for public. Public will lap up. Okay. And opinion, sentiment, and aspect triple is I love song, brother like cast, director like storyline, and public lap up storyline. So the binding of the opinion holder with a particular aspect of the entity is very important. I love song, not the storyline. Okay, and similarly, public will lap up the storyline, not really the cast. So this kind of entity binding, entity relation resolution is very important as a basic NLP task. Now, sentiment analysis is a multi-dimensional problem. If you take different axes, I start with the horizontal axis, which is document, sentence, and aspect. That means the sentiment can be expressed for the whole document, or with a finer granularity on the sentence, or still finer on an aspect of the entity. The sentiment can also be sensitive to the language. We know that languages are culture specific, and expression of sentiment also is culture specific. In CJK countries, China, Japan, and Korea, it is impolite to express sentiment through very strong words. Okay, people use very moderate adjectives and adverbs and verbs, which are carrier of sentiment. On the other hand, in the Bay Area, the west coast of America, almost everything is astounding, amazing, and so on. Okay, so the adjectives are much more intense there. Similarly, the features can be bag of words, which is very simple. You can always do very simple NLP and get the features in the form of bag of words. Then syntactic dependencies require parsing of the sentences. Discourse features need to connect sentences, especially the noun-pronoun resolution is very important there. But as you increase the complexity of the features, the NLP demand also increases. Then the sentiment can be expressed, which is the O axis, through subjectivity or discrete polarity or ordinal value. So subjectivity is subjective or objective. This movie was cast in Kuala Lumpur. This is an objective statement. This movie is nice is a subjective statement. Then discrete polarities, for example, when you have star ratings, 5-star, 3-star, 2-star, and so on. These are called discrete polarities. Similarly, you can have numerical values expressing sentiment, number 1, 2, 3, 4, and so on. So the expression of sentiment can be through discrete polarities, ordinal values, and so on. Coming to the next axis, which is the R axis, the resources for sentiment analysis could be dictionaries, the seed set, and ontology. Ontology is a hierarchy of conceptual structure. And then finally, the algorithm axis would be based on rule bases, unsupervised machine learning, SVM-like classifiers, generative models, deep learning, and so on. So the purpose of this slide is to show that sentiment analysis is really a multidimensional problem involving the language in which sentiment is expressed, multilinguality, features, the granularity of expression, resources, algorithms, and so on. Okay, algorithm is only one component of this very big perspective. The challenges to sentiment analysis are many, and some of them will be illustrated as we go ahead. But there are things like this. Human beings are fond of making oblique statements, okay, indirect allusions, and so on. So I suggest you wear your perfume with windows and doors shut. So this is a sarcastic statement, and the sentiment is negative. But see how interestingly it is expressed. I suggest you wear your perfume with windows and doors shut. The speaker doesn't like the perfume. Then similarly, the next statement, Jadeja falls 284 runs short of what would have been a fourth first-class triple century. Okay, he made only 16 runs, and so on. And then thwarting is another phenomenon which I'll illustrate as we go ahead. And the nature of the text is also very informal. People express sentiment using this kind of funny words, tim, tam, and so on. Okay, and there are lots of emoticons, emojis, whose processing we'll deal with now. And then word senses play an important role. He is a deadly football player is a praise for the person. You may have deadly snakes in the camp at night. This is a negative expression for the camp. So in spite of so many complexities and so many features, learning algorithms, and so on, the basic sentiment analysis flow is as shown in the slide. You have input text, feature is extracted, it is passed through a classifier, and in this process lexical resources may play their role, and then finally the sentiment comes out. Okay, positive, negative, or neutral. So this is the basic flow of sentiment analysis, and maybe for a lot of machine learning algorithms. Now typical features are term presence or absence, frequency of the term, how many times it appears, term position, adjectives in the beginning of a text or at the end of a sentence are more impactful, okay, than their other positions. So part of speech features like noun, verbs, and so on, senses of the words, clusters of words and their IDs, cluster of adjectives, verbs, and so on. All these are important features, and they have been found to be useful over the years. So let's particularly remember the term presence, okay, which is essentially bag of words. So now this is a collection of figures over many different learning algorithms for sentiment analysis. So over the years, people have used many different features. The features are shown in the first column. Unigrams, just presence or absence of words. Unigrams with counts, unigrams and bigrams, adjectives, unigrams and part of speech, and so on. And on the columns we have algorithms. Okay, naive Bayes is a very simple machine learning algorithm, but very effective. Maximum entropy is another algorithm. Support vector machine was very popular a few years back. Now of course deep learning. So now when we look at the NB and unigram combination, the figure which is in bold, so that tells a message. The message is that with a very simple classifier, an extremely simple feature, we get an accuracy of about 80%, and that accuracy is not improved much, okay, as we increase the sophistication of both algorithm and feature. So this is an interesting phenomenon, and it is observed in many other fields of natural language processing. For example, in information retrieval, in word sense disambiguation, very simple things work, okay, and they produce accuracy figures which are difficult to improve upon, in spite of improving the features and machine learning algorithms. Okay, so this is something which needs some amount of theoretical investigation, because this phenomenon is appearing across natural language processing in many different fields. The message is this, that simple algorithms and simple features deliver results which are difficult to improve upon. Okay. Then in this roadmap, there are many topics. I don't think I'll be able to cover all of them. But let me first go into a piece of work about which we are very excited. And this is a very recent investigation with my M.Tech students, Kajal Gupta and Kanchan Pal. And this is on emoji suggestion system. So emojis are here to stay. They are forming part of text very routinely, especially in short pieces of text, tweets, blogs, SMSs, and so on. So an emoji is a graphic symbol or ideogram that represents not only facial expressions, but also concepts and ideas such as celebration, weather, vehicles and buildings, food and drink, animals and plants and emotions, feelings and activities. So for example, celebration has this cake symbol, weather has a sun symbol, vehicle has the aeroplane symbol, building has a structure symbol, food again has a pizza symbol, drink has a glass of drink symbol, and so on. Okay, so these emoticons are very much now part of our vocabulary. And here are for some examples. Traveling to UK for vacation. So there is a plane symbol and also the flag of United Kingdom. I met Dwayne Johnson today. Not only exclamation sign, but also there are two emoticons. Okay, so human mind works in a very interesting way. Maybe one exclamation would have done. Why three? Exclamation and emoticon, why both? And why not only one emoticon? There are two emoticons. Okay, so human beings, I think, believe in excesses, and they want to make their point very, very forcefully, and these are instruments of forceful communication. So now, we find that just like words, our investigation shows this, emojis also have ambiguity. Okay, so you have LOL, then exclamation, you are so funny, and then this symbol of tearful smiley face. Okay, both tear and smile. Got all A's but one. Again the same emoticon. So this emoticon is used in two different senses, funny and happy. Okay, so you can begin to see that emoticons as entities also have ambiguity, just like words. The word bank has two meanings, river bank and financial place. So emoticons also have multiple senses. And we have long history of working on words in disambiguation, and we know, what is the way to deal with ambiguity. I'll come to that little later. Emoticons also have nuances. For example, unamused face is expressed through many of these symbols. Okay, there are multiple symbols to express unamused state of mind. It is just like multiple words representing the same sense. Okay, multiple words. So, for example, joy, joy and delight. Okay, joy, delight, happiness. All these are synonyms expressing the same meaning. So emoticons also have this property. Same sense, multiple expressions. Okay. Then multi-level classification is an important area of machine learning. So emoticons we see are a case of multi-level classification, and there is a very large repository of emoticons. Traveling to UK for vacation, there were two emoticons attached here. Thanks a lot, many exclamation symbols, and then there are again two emoticons. Okay, the clap symbol as well as the heart symbol. Currently there are 2666 emojis in Unicode version 10, and it is difficult for a human being to sift through all these repository of emoticons and place them appropriately, okay, in consistency with the meaning of the sentence. So it needs some amount of automation. This is our main investigation. So the problem statement is this: if the input is a tweet and the output would be one or more emojis, which is appropriate for the context as well as the meaning of the tweet. So we see that there is quite an amount of literature on emoticon processing, okay, emoji processing. So significant pieces of work are Barbieri et al. In 2017, which deals with emoji prediction. It's very similar to our work, but we deal with multi-level emojis. Okay, we can produce multiple emojis. Then grouping of emojis. Then EmojiNet is an important structure which is created in 2016. So I would say that in this decade, people have started doing serious work on emojis. So emoji resource is Emoji Net, just like WordNet for words of a language. So Emoji Net encodes or stores the Unicode, the emoji name. For example, raising hand, the Unicode is U plus 1F64C. There is a short code, there is a definition, 2 hands raised in the air celebrating success. There are keywords corresponding to this emoji, celebration, hand, hooray, raised, images, and then related emojis, then emoji category. These are gesture symbol, just like the hypernymy relation in WordNet. Then there are senses. So these emojis can be grouped or clustered. We have used spectral clustering technique for grouping of emojis. But I think a much more interesting and serious contribution is Emoji Matrix. Okay, we borrow this idea from Watson disambiguation. So when the emojis are clustered, you can see on the first row, all these are unamused faces. And then the dog is expressed by 2 emojis. Music is expressed by many emojis on the right bottom corner. And this is the expression of one thought by multiple emojis. All of them are clustered. But each emoji is ambiguous, as I said, ambiguous in the sense of multiple words being attached to this emoji. So the emoji symbol of smile has words associated: smile, happy, joy, and green. So emojis with their corresponding keywords are taken from this emoji net. Now emojis do get clustered. For example, if you look at this clustering of emojis on this XY plane, then fourth cluster expresses love. So there are many different symbols which express love. Music is cluster number 3. Again, there are many emojis there. Okay, so emojis do get clustered. But this idea of lexical matrix being used to emoji is a novel idea, I think, and we believe it is a useful idea. So in Watson's disambiguation, lexical matrix plays a very fundamental role. We have word meanings in the form of M1, M2, M3, etc. And the word forms are in the columns. Okay, rows are word meanings, columns are word forms. So the word bank has the sense of dependence, which is M1. So that is expressed by 2 words, bank and depend. Bank in the sense of finance is M2. Bank in the sense of side of water body is M3. So columns are words and meanings are rows. So this is a very nice abstraction to capture word forms and their senses. We borrowed this idea and created what is called Emoji Matrix. So the keywords are joy, sweet, celebration, clap, and so on. And corresponding to joy, there are these emojis on the column. So only one of them is 1. Only one entity in that row is 1. So joy and that smiley face has a correspondence. Okay, but if you take the row number 3, which is celebration, then there are many ones in that row, which means that celebration is expressed by multiple emojis. Okay, so this is a good abstraction. We call it Emoji Matrix, and we'll see its application very soon. So our goal was to output emojis, one or many, given the tweet as an input. So data set that we used had tweets from 360 users. Total number of tweets that we gathered were 900,000. Out of them, emojis were in about 1.4 lakh tweets. The number of most frequent emojis considered were 137. The training set was 82,000 about, validation set was 2,000, and test set was 2,000. This I am reporting as a necessary ritual for any kind of machine learning scenario. In machine learning scenario, we have to report what our data is for its authenticity. So used first statistical classifiers, and we wanted to verify one hypothesis, that emojis do make a difference or not. Okay, if we plug in emoji, then do the accuracies improve? That was the first question, first basic question to be answered. So we used many different kinds of classifiers, Bernoulli, naive Bayes, linear SVC, logistic regression, and so on. So if I take, for example, logistic regression, then logistic regression alone gives an accuracy of about 0.19, F score 0.19. But logistic regression with emoji clustering the accuracy improves to 0.23. And if we use the emoji matrix, which I mentioned some time back, then the accuracy moves to 0.24. Okay, slight improvement, but we do see a trend of emoji matrix always making a difference when we use emoji and when we don't use it. Okay, so emojis are useful. This is the fact that is established. Now the trend these days is to use deep learning networks. So in deep learning network, the important tools are convolutional neural network, LSTMs, feed-forward network, and so on. Okay, all of them are individually very interesting and successful machines, but researchers of machine learning, users of machine learning, would benefit from noting an important point I want to make. This CNN, LSTM, FF, okay, CNN, LSTM, and feed-forward network, this pipeline is a very effective pipeline, and I think it is here to stay. The reason is that it has an important philosophy. So CNN does feature extraction, LSTM encodes memory, and the feed-forward network makes the ultimate decision. Okay, so this pipeline of machine learning in deep neural network is a useful mechanism which the students of machine learning would do well to remember. So the CNN component of the pipeline does feature extraction. There is a window which slides over the words, okay, and captures the features, and then the LSTM takes word by word and its encoding, and then passes this information, the encoded information, to a feed-forward network which makes the decision. Okay, so this feature extraction, memory, and decision-making pipeline is an important point to note. So there are different pieces of information on the DNN part. There are many numbers like the filter size and the encoding, the LSTM layer. I don't think I have time to go into all that, but I'd like to present the results. So if we have CNN, LSTM, and the feed-forward pipeline with static and non-static updation of weights, then the F-score is 0.21 and 0.22. Now when we use emoji clusters, then the F-score improves to 0.25. Okay, and if we use emoji matrix, then the F-score is 0.27, which is the highest value we have obtained, okay, in this pipeline. Now there are some case studies to illustrate what is the role the clustering and emoji matrix are playing. The exact emojis which are output, the cases of exact match in the output emoji and the gold standard emoji, this is the first case. Happiest of birthdays to you, your Twitter weirdos love you so much. So this is this cake or ice cream symbol, or maybe the cone symbol, which is produced by the program, and this matches exactly what was there inside the tweet. And then the next one really lack natural beauty, and that is funny as hell. Then you have number of symbols here, and the program produced exactly those emojis. These are exact matches. Have an amazing night, 2 heart symbols, exact match. And these case studies are apparently incorrect. That is because the gold standard emoji doesn't match the predicted emoji. But when we group them through clustering, then the result is correct. So the actual emoji is, I wonder why he deleted his tweet. So actual emoji is as shown in the first line, the predicted emoji is the other one, but they actually form a group, they actually form a cluster. We need to celebrate this day. Then the actual emoji was this cone symbol, predicted emojis were 2. Remember, ours is a multi-level classification, and the actual emoji and predicted emoji have a subset relationship between them, and then they can be looked upon as correct. And when we do emoji grouping through the emoji matrix, then the results improve further because the interrelationship between emojis are much more coherently captured in the matrix. Okay, so even though the predicted emoji is different from the gold standard emoji, we can detect that they are actually same because of the emoji matrix. But one interesting point was that a lot of emojis are used for sarcasm. Okay, and sarcastic cases were the cases where our program failed completely. Okay, that is because sarcasm is a very difficult problem. If you look at this sentence, well, there it is. I am like really smart. Okay, okay, really smart. And so, how many minutes now? 10 minutes. Okay, so this is a sarcastic statement, and the software failed to capture this. So I'll quickly go to sarcasm and sort of rush through this. We have done many years of work, okay, on sarcasm, and probably a pioneering group in this very difficult problem. So the word sarcasmus comes from the Greek word to tear flesh with teeth. Okay, so that means sarcasm is always meant to hurt or injure. So sarcasm is a kind of irony. Irony is not always hurtful, but sarcasm is always hurtful. And there are many different kinds of sarcasm. One kind of sarcasm is through the body language. It is called elocutionary sarcasm. Ooh, wow, well done. Okay, this is an expression of appreciation, but look at the face. Okay, so the body language and the words are in incongruity with each other. So what our contribution was is that we captured sarcasm through a linguistic instrument called incongruity. Now sarcasm is very difficult to capture, but it also has lots of clues embedded on the tweet. Okay, so haha, you're very smart, and then an emoticon. Your intelligence astounds me. You have LOL. Then there is heavy punctuation. Protein shake for dinner, 2 exclamation, great, and then 3 exclamations. Okay, so these characteristic of sarcastic statements, it is important to capture those clues. But our contribution was capturing incongruity. So I love being ignored. Love is a positive sentiment word, ignore is a negative sentiment. 3 a.m. at work is not a very desirable situation, but EAA is positive. So the presence of positive and negative sentiment together indicates sarcasm, and we have captured that in our algorithm. So incongruity can be explicit, I love being ignored, for example, and it can be implicit. I love this research paper so much that I made a doggy bag out of this. In this case, the sarcasm is through an implicit negative emotion. So we have captured sarcasm through word embedding and deep learning, and one of these pieces of work were very widely reported. MIT Technology Review carried this article, How Vector Mathematics Helps Machines Spot Sarcasm. ACM Technology Review also carried an article on this. So as I mentioned in the beginning, the feature sets are from basic sentiment analysis, unigrams, bag of words. Then sarcastic text also has a lot of emoticons, capitalization, punctuation marks, they have to be captured. We capture incongruity through word embedding and their similarity. And there are data sets which are standard. So our result shows that we are able to capture sarcasm quite effectively. All these accuracy figures in bold are our figures. Okay, they are vast improvement over what was available in the area at the time. So incongruity and embedding, they are captured by similarity computation. This is from an actual corpus. A man needs a woman, like a fish needs bicycle. Okay, so this is a sarcastic statement. Now the similarity between man and woman is 0.766, fish and bicycle, very little similarity. But there is a preposition like. So the two pieces of text before and after preposition should have similar property. That property similarity is violated, okay, as we capture through word embedding. So this shows that this sentence is sarcastic. So I'll quickly jump to there are many results based on deep learning, and everywhere we have shown improvement because of use of incongruity. Thwarting is a very interesting phenomenon which I'll skip, but I'll go to cognition based sarcasm detection. Just a minute, just 1 minute. Yes, so in natural language processing, we know that there is language axis, then algorithm axis, and the property axis. Then when you make use of eye tracking, you can capture the movement of the eye, and that is a very important clue for decision making. Okay, so what we did was we captured the eye of a person when he is reading the piece of text. This technology will become real, okay, very soon, because the mobile devices come with eye tracking technology. So the eye moves over the text, and if we track the movement of the eye, then the interesting patterns are seen. For example, for sarcastic sentences, we have seen that the eye always has a lot of back and forth movement. I will always cherish the original misconception I had of you. This is a sarcastic statement. Cherish is positive, misconception is negative. So this particular phenomenon is captured through eye tracking, and we pass the eye tracking feature along with textual features to a deep learning network. Okay, and our results again show that we get about 70% accuracy, which is a major improvement over state of the art. And the feature ablation shows that the duration of the eye fixation, okay, is an important feature. So this is the neural network which is used with static and non-static feature augmentation. So eye tracking features are augmented to textual features. So in sarcasm detection, we achieve 70% accuracy, which is quite impressive. Okay, so I think I'll draw some conclusions now. There are many different facets of sentiment analysis, and the advanced problems are emoji recognition, sarcasm detection, thwarting, cross-lingual sentiment analysis. And the conclusions are the following. Sarcasm is an important problem, and it draws heavily from sentiment analysis. Sentiment analysis again draws its foundation from natural language processing, which is a part of AI. General sarcasm analysis does not work well. The general sentiment analysis doesn't work well for sarcasm detection. Rich feature set is needed. Surface to deeper intent is to be captured through incongruity. Data and annotation play an important role. Deep learning is producing good results in sarcasm detection. Emojis can be treated like words. Okay, so this is an important finding. Emojis are like words; they have their senses and ambiguity. Now, the future work consists in mining the web for more training data, explaining the features which are discovered in deep learning, which is part of explainable AI. Multilinguality, multimodality, social media are important problems for sentiment analysis. And humor, sarcasm, and fake news have one important common platform. If we can deal with incongruity, we can tackle all these problems together. Humor, sarcasm, and fake news. And there is one phenomenon which is like sarcasm, that is called humble bragging. Okay, humble bragging is, my life is miserable, I have to sign 1,000 autographs every day. Okay, this is called humble bragging. So there again you have positive and negative sentiment together, but it's not sarcasm. Okay, so sarcasm algorithms have to deal with this, and we have to enrich the decision making process by making use of emojis, pragmatics, and emojis. So everything I said is through my publications. They are available from my homepage in publication, and there is this survey paper also. And thank you.
We might have time for just one question, maybe.
Yes.
Hello, sir. This is Akhilesh. I'm a data scientist at Takara Labs. So my question was, so it's interesting how you didn't mention attention mechanisms here. So firstly, have there been experiments on that in this regard? Second, just wondering what happens if you sort of eliminated the CNN and just use pre-trained word embeddings to an LSTM directly?
Yeah, CNN we know has this sliding effect on the words, and CNN is essentially a replacement for n-grams. Okay, so it is n-gram extraction plus additional features from that n-gram. So CNN plays that role essentially. Okay, so thank you.